In this lecture, we are going to talk about center of mass. Although we had started about it in the last class, it was a bit early, it was a bit fast. So we will try to repeat it. Motion of the center of mass, and maybe if time permits, we will take the rocket motion towards the end. So, what is a center of mass? The center of mass is a mass weighted average position of the particles. So if there are a number of particles scattered of different masses and we want to find out what is the average position of the masses, then we and if you find the mass weighted average position, that means the average position will turn towards the heavier mass, then such a position is called center of mass. The most beautiful thing about center of mass is that if you have a homogeneous body that has a geometric center such as the center, then the center of mass is at its geometric center. Example, a spherical billiard ball or a sugar cube. You will get, these are all symmetrical bodies, and the center of mass is at the center. Even if you don't have a 360-degree symmetrical body, even if it has one axis of symmetry, then the center of mass always lies on that axis. Example, a wheel or a pulley. Center of mass can be outside the body as well. For example, a ring. A uniform ring's center of mass lies at its center, which is not the part of the body. So in this diagram, we have number of masses m1, m2, m3, and they have coordinates x1, y1, x2, y2, x3, y3, etc. And xcm, ycm is the center of mass. xcm, ycm is the center of mass. So how do you get xcm, ycm when the others are known? So we know these equations. For a system of discrete particles like this, the center of mass position is m1 x1 plus m2 x2 plus m3 x3 upon plus dash dash, for summation runs over all the particle, upon the total mass. So sigma mi xi, and here it is divided by sigma mi. Y coordinates in a very similar way, sigma mi yi upon sigma mi. Center of mass can be real or virtual, that we have already discussed. Now, instead of x and y, if the position vectors are given, then each position vector r, say r1, can be written as x1 I cap plus y1 j cap. R2 can be written as x2 I cap plus y2 j cap, etc. Therefore, the position vector for the center of mass can be written in a very similar form. R vector R for center of mass is m1 r1. Remember this, notice this is vector r1, m1 vector r1 plus m2 vector r2 dash dash upon total mass, or mi ri, where ri's are vectors, upon total mass. If it's a continuous mass distribution, a rigid body, then we have to take an integral of r dm upon total mass, which is rcm. When we solve some problem, we will see the applications of these formulae. What will be the velocity of the center of mass? So velocity is time derivative of position. V is dr by dt. So we can take the r equation and take its derivative with respect to time. That will give me the velocity equation. So if you do that, you will get a very similar equation. Velocity of center of mass is m1 v1 all in x direction plus m2 v2 plus m3 v3 upon m1 plus m2 plus m3 dash dash, which is total mass. And similarly you will get for a y component m1 v1 plus m2 v2, all the v1 v2 v3s are in y direction upon the total mass. If you take the derivative of the position vector of the center of mass, you will get velocity vector. So if you take the derivative of r vector, you will get the v vector. So all these are now vector quantities. Formula have the same form as earlier. Denominator has the total mass. The total mass can go up and multiply on the left side. It will become mv center of mass, which is m1 v1 plus m2 v2 plus m3 v3. But look at this. m1 v1 is the momentum of the first particle. m2 v2 is the momentum of the second particle. m3 v3 is the momentum of the third particle. Summation runs over all the particles. So the right hand side is nothing but momentum of all the particles taken together. So m v of center of mass, that means the total mass into velocity of center of mass, gives me the total momentum of the particle. So let's take that equation once again and go ahead. So acceleration is the derivative of the velocity. So if I differentiate this equation once again, then I will get my acceleration. So derivative of v here will give me acceleration of center of mass. Derivative of v here will give me the acceleration of the first particle, so on and so forth. So this equation can be written as ma center of mass is equal to m1 a1 plus m2 a2 plus m3 a3 plus dash dash dash. Now ma is nothing but the net force acting on the particle. So ma is nothing but sigma f. But sigma f is nothing but the total of all the force, that is the external forces as well as the internal forces. Both these forces are working. But we know that by Newton's third law, all the internal forces are zero. Therefore, only external forces will determine the motion of center of mass. So this is a very important result. Uh, it tells us that the internal forces does not matter. So that is why, suppose if a vehicle like a train is moving, but if you walk in the train, or uh, if you're sitting in the train, if you jump in the train, the motion of the train is not affected by the interaction between you and the train, because any force that you will exert on the train or that the train will exert on you will all belong to the category of internal forces, and that will cancel off, and what remains is only the external force. Another example is if you catch a ball, then the motion of the ball, the impact that you receive from the ball, everything is decided by the external forces and not by the forces which are internal to the particles which constitute the ball. So when a body or a collection of particles is acted upon by external forces, the center of mass moves just as though all the mass were concentrated at that point. That point here will be the center of mass. And it were acted upon by a net force equal to the sum of the external forces on the system. So all the internal forces, internal interactions of the points will cancel out because of the Newton's third law. And the only thing that will matter are the external forces. So this leads to the concept of center of mass, and in fact we are using it from the chapter of Newton's law onward. We are replacing each body as a point mass. We are only looking at the forces which are external and acting on the body from the chapter of Newton's laws. We are not looking at internal forces, and we are always taking the body as the point mass. There we said just take the body as the point mass when you draw your free body diagram, but here is the reason why we do that. We do that because the internal interaction of the particles of the body or internal forces do not matter as long as the motion of the bodies are concerned. The motion of the body is completely governed by forces which are external to it. So sigma f external is equal to ma of center of mass, while sigma f internal will be 0. So here are two examples I will give. This is a rocket shell. It could be a Diwali rocket or anything. It has been projected. You know that it will follow the parabolic path. But suppose it explodes somewhere in the middle. One key question is asked at where the two parts will go. So if it's exploding, all the chemical forces are internal to the system. So center of mass motion will remain unaffected by the internal forces. They all will cancel out. So the shells will move from this point onward. Shells will move in such a way that the center of mass always remains its original position. That means it would stay at a position where it would have been if the shell would not had exploded. So one fragment will go in this direction, other fragment has to go in the opposite direction so that the center of mass remains at its chartered path. So this is one of the example. Other example is this. This is the firework picture from the Beijing Olympics. So here you can see that as the fireworks explodes upward, the center of mass will move in the upward direction, and as the firework particles they fall down, the center of mass will come down. So the next topic is the rocket motion. This is the example of a rocket, Space Shuttle Atlantis.
Firing chain is armed. Sound suppression water system activated. T-minus 10, 9, 8, 7, 6, 5, 3, 2, 1, 0. And liftoff of Space Shuttle Atlantis on a mission to build, resupply, and to do research on the International Space Station.
Houston now controlling. Atlantis begins its penultimate journey to shore up the International Space Station.
So this is the motion of the rocket. Typically, when we ask how does a rocket move, then the normal answer is it moves using the third law. There is an exhaust of gases which is pushed downward, and the rocket gains momentum in the forward direction. So let's try to see how does an analysis of rocket motion goes. So I have a rocket which at time t has the velocity v in the positive x direction, and its initial mass is m. Now as the rocket accelerates, it will it will exhaust out some of the material, so the mass will decrease and velocity will increase. So at time is equal to t plus dt, let its velocity be v plus dv, and its mass will be m minus dm. This dm mass is exhausted out in the form of gases towards the backward direction. Let Vx be the speed of the exhaust gases with respect to rocket. I repeat, Vx is the speed of exhaust gases with respect to rocket. With respect to ground, therefore, the speed of the exhaust gases I will write as speed of fuel which is expelled. Speed of fuel will be v minus vx. So rocket is moving to the right and vx is towards the left. So the speed of the fuel as seen from the ground will be v minus vx. Since the rocket generally moves at a very high speed, this quantity is still positive and it still may be towards the positive x direction. As time increases, the mass of the rocket decreases because the exhaust gases are expelled. So dm is a negative quantity. Please remember this. We will use this towards the end. Dm is typically called as change in mass, which is final mass minus initial mass. Since final mass of the rocket is less than the initial mass, dm is negative. I repeat, V exhaust or Vx is the velocity of exhaust relative to rocket. So if you're sitting on the rocket, for you the speed of exhaust is Vx, but if you're sitting on the ground, then the speed of exhaust is V minus Vx. So let's go ahead and do this small derivation quickly. So at time t, what is the momentum of the rocket? So its mass is m and velocity is v. So the momentum of rocket is mv, or momentum of your system is mv. At time t plus delta t, you have fuel which has been expelled. So the velocity of fuel is v minus vx, as we have discussed. Momentum of fuel is mass of fuel into velocity of fuel. Mass of fuel is dm, velocity of fuel is v fuel. So dm into v fuel, which is dm into v minus vx. Momentum of rocket is, now the mass of the rocket has been reduced by amount dm. So the new mass is m minus dm, and its velocity has increased by dv. So the new velocity is v plus dv. So this will give me the momentum of the rocket. This is momentum of the fuel. So the momentum of the system after time dt is sum of these two quantities. So this is the momentum of the rocket after time dt, and this is the momentum of the fuel after time dt. So if I add the two, I'll get the total momentum. So the equation 1 gives me the total momentum at time t before a certain part of fuel is exhausted. Equation number 2 gives me the total momentum at time t plus dt when the fuel is exhausted. Since there is no other, I assume that the rocket is in deep space, there is no gravity, nothing else is working. So in this case, total initial momentum has to be equal to total final momentum. That means these two must match. So if that happens, then mv is equal to m minus dm v plus dv plus dm v minus vx. So I can take this and put it here. Here I can open this bracket and I can open this bracket. So m into v is mv, then m into dv is mdv, minus dm into v is minus vdm, and then minus dm dv, then plus vdm, and then minus vx dm. Now certain quantities will cancel out. So mv is on both sides, it will cancel. Minus vdm and plus vdm will cancel. This is negligible. dm is very small, dv is very small, total is negligible. You get mdv and minus vx dm left. So if you bring this on the left side, you will get mdv is equal to v exhaust dm. That will give you the gain in the velocity. The gain in the velocity dv is v exhaust upon m into dm. Once you know the gain in the velocity, you can calculate the acceleration by dividing by dt. So acceleration is dv by dt, which is v exhaust by m dm by dt. Force is mass into acceleration. So take the acceleration point, multiply by mass. Mass and mass will cancel. You get F is equal to V exhaust dm by dt. So this gives me the change in velocity, acceleration, and force, or the thrust of the rocket engine. All three quantities I can derive. I can use this to find out the total change in the velocity. So this equation I will rewrite. dv is equal to vx upon m into dm. At t is equal to 0, let's say that at some time t is equal to 0, velocity is equal to v0 and mass is equal to m0. I can integrate this equation between the limits v0 to v and m0 to m, assuming that the exhaust speed remaining constant. Therefore, the left hand side is v minus v0. And remember that dm is negative. Please recall, I had told you in the beginning that as the time progresses, mass decreases. So change in mass, which is final minus initial, is always negative. So a negative sign will appear here. And the integration of 1 by m dm is natural logarithm of m, which if you put between the two limits, you will get natural log of m by m0. Minus sign I can absorb inside and I will make it m0 by m. So this gives me the velocity as a function of mass, that how much mass is there left in the rocket and how much velocity will it gain, where m0 is typically the initial mass when the rocket is full, it has a lot of fuel, and m is the final mass when the rocket have exhausted a lot of fuel from it. So small m is less than m0.